Hello students, in the last lecture I was discussing about ionic equilibrium. As we know that ionic equilibrium deals with ionic reaction, and when we discuss an ionic reaction that must be reversible, then only we can apply the concept of equilibrium. For example, dissociation of acetic acid. So, this is CH3COOH. When you put in water, it dissociates to give you acetate ion and H plus ion. So, reaction has ions. First thing is reaction has ions, and the second thing is there is a equilibrium. Between your undissociated species and dissociated ions. Only in this case we can apply the concept of equilibrium. So, when we apply concept of equilibrium to an acetic acid solution, we can simply write the way we used to write for your any equilibrium reaction. Equilibrium constant equal to products. So, this is the multiplication of the ions in the product side divided by the concentration of reactant. So, first thing is ions, and what I discussed in last lecture is ions are generated by electrolytes. So, when you put electrolytes in aqueous solution, ions are generated. Electrolytes, generally we discuss three different kind of electrolytes. One is acid, another is base, and then salt. Now, second part is reversible. Not all ionic reactions are reversible. Not all ionic reactions are reversible. Lot of them are irreversible. For example, your dissociation of a strong acid. For example, HCl. This completely dissociates. It means it is almost irreversible to give you H plus ion and Cl minus ion. So, when the reactions are not reversible or reactions are irreversible, we cannot apply the concept of equilibrium here. Similarly, we can think of dissociation of strong bases. For example, NaOH, sodium hydroxide. When you put in aqueous solution, it will give Na plus aqueous plus Cl minus aqueous. And the last one is your dissociation of soluble salts, for example, NaCl. This is also irreversible. This gives you Na plus aqueous plus chloride ion aqueous. So, dissociation of strong acids, strong bases or soluble salts are irreversible, and we cannot apply the concept of equilibrium. Now, where we can apply? We can apply for dissociation of weak acids, For example, your acetic acid. So, it breaks to give you CH3CO minus aqueous plus H plus ion aqueous. So, this is your reversible reaction, and we can apply equilibrium constant. Here we are writing equilibrium constant for this reaction, which is known as acid dissociation constant. And this will be equal to your CH3CO minus into H plus by acetic acid, concentration of acetic acid. Similarly, we have dissociation of weak bases. For example, you have ammonia solution. In water, it will give you NH4 plus, aqueous plus OH minus aqueous, and then again we can write K. Here we can say this is base dissociation constant, and that is equal to ammonium plus OH minus by NH3. So, this is the way we can apply the concept of equilibrium. The third example is your solubility of sparingly soluble salt. For example, AgCl. AgCl will give you Ag plus Cl minus. So, this is in aqueous, this is in aqueous form. These three types of dissociation are reversible. If we take for example, AgNO3, then it is not reversible, because this is a soluble salt, and this will give you Ag plus aqueous plus NO3 minus aqueous. It completely dissociates. It is soluble, it completely dissociates and gives you silver plus aqueous plus NO3 minus aqueous. Whereas, if I take another salt AgCl, this is a sparingly soluble salt, and it will give you Ag plus aqueous plus Cl minus aqueous. So, only a small amount of AgCl will go to solution, whereas almost all AgNO3 will go to solution. So, now we know that how ions are generated and when we can apply the concept of equilibrium. So, let us go and discuss your degree of dissociation. This will be the term which we will come across quite often when we are dealing with questions of ionic equilibrium. So, degree of dissociation is your moles of your acid, base or salt, which exist in ionic form, per mole of acid base salt. Base or salt. For example, if suppose I take 1 mole of acetic acid and I put in water, it will give you CH3CO minus plus H plus aqueous. So, I started with 1 0 0, some of the mole will go in aqueous form. The number of mole, the amount in mole which goes in ionic form is called your degree of dissociation. For example, if alpha mole of acetic acid goes to your ionic form, what does that mean? That alpha mole of acetate ion will be formed, alpha mole of H plus will be formed, and what we are left with is 1 minus alpha. So, alpha mole of acetic acid has gone to ionic form and what is left here is 1 minus alpha, and the ions generated are alpha mole of acetate ion and alpha mole of H plus ion. So, this is the degree of dissociation. Here alpha is the degree of dissociation, since alpha mole out of total of 1 mole of acetic acid has gone to solution. So, suppose I take another concentration CH3COH going to CH3CO minus plus H plus. I started by C 0 0, then we know that alpha is your amount of CH3COOH which has gone to ionic form per mole of CH3COOH acid or acetic acid. So, if alpha is your number of mole per total mole of acetic acid, so you have C alpha is the used of acetic acid. Okay. And so, we can simply write the remaining acetic acid as C minus C alpha. So, what we simply multiplied, since alpha is per mole and we have C number of moles of acetic acid. So, if 1 mole gives you alpha mole of your ions, C mole will give C alpha mole of ions. So, C minus C alpha, and here you will generate C alpha, and another way to write is C 1 minus alpha, C alpha. Now, we can write Ka in terms of your initial concentration and degree of dissociation, which is alpha. So, how we will write? We know that this is acetate ion into H plus divided by your CH3COOH, and since this is C alpha into C alpha divided by C 1 minus alpha. So, we can express Ka in terms of your alpha, which is degree of dissociation for acetic acid. So, let us again write this equation CH3COOH giving you CH3COO O minus plus H plus, what you are left is C 1 minus alpha, and here you will get C alpha. So, Ka is equal to your C alpha into C alpha by C 1 minus alpha, and this is C square alpha square by C 1 minus alpha. Since this is a very weak acid, 1 is quite greater than alpha. So, 1 minus alpha, what does that mean is 1 minus alpha is almost equivalent to 1, and so Ka will be written like C square alpha square by C 1 minus alpha is 1, and so C cancels out C alpha square, C alpha square. So, Ka is equal to C alpha square. So, if I know alpha, I can calculate Ka, and similarly if I know Ka, I can calculate alpha. What will be the alpha? Alpha is simply Ka by C, Ka by C. If we remember, alpha C is equal to H plus ion, and so we can also calculate H plus ion concentration if we know Ka, and that is simply C into alpha, or C into H plus is C alpha, C into alpha is Ka by C, and so you have Ka into C. So, if I know alpha, I can calculate Ka. On the other hand, if we know Ka, then we can calculate alpha, and also we can calculate the concentration of ions in the solution. For example, in this case I have shown you that how H plus ion concentration can be calculated. Now, similarly, we can take another example of your weak base. For example, we can start with ammonia solution. NH4 plus aqueous plus OH minus aqueous. So, Kb is equal to, similarly here we can write C 1 minus alpha, this is almost constant, C alpha, C alpha. So, C alpha into C alpha divided by C 1 minus alpha, and again since it is a weak base, we can simply write C square alpha square by C, or C alpha square. So, alpha is equal to Kb by C under root, and now you see OH minus is what? OH minus is equal to C alpha, and so you have Kb into C. So, you can calculate OH minus concentration if you know the value of Kb, if you know the value of Kb. Now, let us go and discuss about salt hydrolysis. Before that, let us discuss about dissociation of water. So, water is also a weak electrolyte, and it gives you in the solution H plus OH minus ion. You can also write H2O plus H2O giving you H3O plus OH minus ion. Okay. So, K is equal to, we can apply equilibrium concept, K is equal to H3O plus into OH minus divided by H2O square. And this is a constant. So, K into H2O square is also known as Kw, and this is equal to H3O plus into OH minus ion, H3O plus into OH minus ion. So, Kw is equal to H3O plus into H3O plus into H minus ion concentration, and this is equal to 1 into 10 to the power minus 14, 1 into 10 to the power minus 14 your mole square dm minus 6, and 8 this is at 300 Kelvin, 298 Kelvin basically for pure water, So, Kw value, this is also known as ionic product, its value is 1 into 10 to the power minus 14 mole square per dm 6 at 300 or 298 Kelvin, let us write 298 Kelvin for pure water. Now, let us think of, take a simple example of pH. If suppose I need to calculate pH of 10 to the power minus 2 molar HCl. Okay. So, first we need to know H plus ion concentration, since your H plus ion is pH is your minus log H plus. So, what is the H plus ion concentration? So, H plus can come from HCl, and we know that HCl is a strong acid, it completely dissociates. So, if you have started with 10 to the power minus 2 molar, you will get 10 to the power minus 2 molar H plus ion from HCl. We can also get H plus from H2O, but this is a reversible reaction, and the amount of H plus obtained will be small. It is to the order of 10 to the power minus 7. Certainly, it will also depend on your common ion effect. It is not exactly equal to 10 to the power minus 7 in presence of HCl. Okay. It will be even smaller than 10 to the power minus 7 because of common ion effect, which I will explain you later. So, 10 to the power minus 7 and 10 to the power minus 2, this concentration is quite less in comparison to 10 to the power minus 2 molar, and hence almost all of H plus in the solution will be contributed by HCl, and so the H plus ion concentration will be 10 to the power minus 2, 10 to the power minus 2. And so, pH will simply be equal to minus log H plus, which is minus log 10 to the power minus 2, and that is equal to 2. So, pH of 10 to the power minus 2 molar HCl will be 2. But now, let us take another example, pH of 10 to the power minus 8 molar HCl. In this case, what will happen? Again HCl will completely dissociate, and so if you have started with 10 to the power minus 8 molar, you will get 10 to the power minus 8 molar H plus, molar H plus. However, here we cannot neglect the dissociation of H2O. H2O. Since H2O will now, which is almost minus 7, is now no longer smaller than or can be neglected compared to your 10 to the power minus 8 molar, because 10 to the power minus 7 is greater than 10 to the power minus 8 molar. So, in this case H2O will contribute to the pH, or H2O contribution of H plus from H2O will not be negligible. In this case, we must add H plus from HCl and H plus from H2O. We must add this to know exact amount of HCl or H plus ion, exact amount of H plus ion. You see, if we have neglected H2O, then what will we get H plus ion? 10 to the power minus 8 molar. And if we calculate pH, then it will be equal to 8. It will be equal to 8, which is not right. Which is not right. pH is equal to 8 is not right. So, pH of an acid, acidic solution can never be greater than 7. So, how can we calculate the H plus ion concentration? So, H plus ion is almost equal to 10 to the power minus 7 plus 10 to the power minus 8, which is around 10 to the power minus 7, 1 plus 0.1, and then you can calculate pH by using minus log H plus, which is almost around 6.9 something. So, you must remember that H plus ion can only be neglected, H plus ion from water can only be neglected when it is your concentration of acid or base is quite greater than 10 to the power minus 7 molar. Now, let us take polyprotic acid. For example, H2SO4. H2SO4. Now, this polyprotic acid, the first step can be very. So, first dissociation is almost irreversible, or K value will be your large, very large. However, the second one will be irreversible. May have some irreversibility. It will dissociate lesser than the first one, So, Ka1, this is called Ka1, this is the first dissociation, and there is a Ka2 which is the second dissociation. So, Ka2 will always be less than Ka1, and it is quite simple. First, you are removing H plus ion from this H plus ion from a neutral species, where in the second case you are trying to remove H plus ion from a negative species. Removal of positive ion from a negative species is really tough. It is not that easy process, and so Ka2 is going to be small. So, we have discussed strong acid, strong base, your soluble salt, weak acid, weak base. Now, we will go for salt. Okay. Again I told you that salt can be of two types, soluble, insoluble, or we can say sparingly soluble, soluble. Soluble will completely dissociate in the solution, completely go to the solution, dissociate, it goes into solution and completely dissociate. Solution, whereas sparingly soluble, a small amount goes and then dissociate. So, for example, AgNO3, if you put in water, you will get Ag plus aqueous plus NO3 minus aqueous, and this is a irreversible reaction. It means it is AgNO3 is completely soluble, it is in solution and gives you ions. It completely dissociates to give ions. Whereas, if you take AgCl, it does not go into solution, only a smaller part goes to solution, and that is what we have discussed. First, I will discuss soluble salts. So, hydrolysis of soluble salt, hydrolysis of soluble salt. There are 4 different type of we are going to consider. First is your salt of strong acid and strong base. Second, salt of weak acid and strong base. In first case, we will take the example of NaCl. The second case, we will take CH3COONa. So, sodium salt. So, this is a strong base and this is weak acid. Now, third case, discuss salt of your strong acid and weak base. Weak base, and fourth we can discuss salt of weak acid and weak base. So, here example is your NH4Cl. So, it is a salt of HCl, which is a strong acid, and ammonia solution, which is a weak base. And last is this is your sodium acetate, ammonium acetate. So, this is weak acid, this is your weak base, salt of these two. So, let us discuss first your salt of a strong acid and a strong base. And we will also discuss, first we will discuss how they will behave, and then we can discuss what will be the pH of the solution if we have a salt of a strong acid and a strong base. So, first thing is this is your salt, which is a salt of a strong base, sodium hydroxide, and a strong acid, which is your hydrochloric acid. We know that this is a strong electrolyte. All soluble salts are a strong electrolyte. So, we can simply write Na plus Cl minus. And now, how Na plus behaves in water, in presence of water? It simply gets hydrated, Na plus aqueous, and Cl minus again H2O Cl minus aqueous. So, whatever H plus ion will get in this solution will come from water. And at 298 K, we know that Kw is equal to 1 into 10 to the power minus 14 mole square dm minus 6. Okay. So, your H plus ion or OH minus ion will be equal, and that will be under root Kw. Since we know that Kw is H plus into OH minus square, and so it is can be simply write H plus square. So, H plus ion concentration will be equal to 1 to the power minus 7 molar, and so pH will be here simply 7. So, for any solution, aqueous solution of a strong salt, salt of a strong acid and strong base, pH will be 7. Now, take the second case, salt of weak acid and a strong base. For example, sodium acetate. Sodium acetate. So, sodium acetate is salt of acetic acid, which is a weak acid, and sodium hydroxide, which is a strong base. And I told you that this is a soluble salt, and so it will completely dissociate into water. So, CH3CO minus plus Na plus. Now, if you remember that last time I told you about behavior of ions in the solution, in aqueous solution. So, let us remember Na plus water. What will happen when Na plus is in water? It will give you Na plus aqueous. Na plus aqueous. What about CH3CO minus? This ion simply does not get hydrated. What it does? It will give you acetic acid plus OH minus ion concentration. And the OH minus concentration which you are going to get in most cases is always greater than OH minus which you get from water. And so, if I want to calculate pH or pOH, I need to know what is the value of OH minus. So, let us consider again this reaction CH3 CO minus plus H2O giving you CH3 COOH plus OH minus. So, this is your reaction, and now I need to calculate what is the OH minus ion if I know acid dissociation constant of acetic acid, which is a weak acid. So, let us write Kh, which is hydrolysis constant. This is known as Kh. Equilibrium for this reaction is called Kh, since this is a hydrolysis of your salt. So, Kh is equal to CH3 COOH into OH minus divided by CH3CO minus. Now, again if I assume that your C is the concentration of salt, then C will be, since this is a again soluble salt. So, this is simply sea salt, initial concentration is sea salt, and if I take that this reaction is this alpha, and we will get C alpha, C alpha. What does that mean is, out of 1 mole of CH3COO minus ion, alpha mole has converted to your CH3COH. In this case, we can just write simply this equation, and we can put it here C alpha by C 1 minus alpha. Okay. So, KH is acetate ion OH minus, acetic acid OH minus, CH3CO minus ion, or you can express in terms of alpha also. Now, let us write KH is what? KH is CH3 COOH into OH minus divided by CH3 COO minus ion. Okay. CH3 COO minus ion. And we also know for acid dissociation constant of acetic acid, this is CH3 COO minus H plus by CH3 COOH, CH3 COH. Now, let us multiply KH into Ka, what you will get? KH into Ka is your CH3 COOH into OH minus by CH3 COO minus into CH3 COO minus into H plus by CH3 COOH. So, this cancels out, this cancels out, this cancels. So, this is simply equal to Kw. So, Kw is equal to your KH into Ka. So, we know Kw, we know Ka, so we can calculate Kh, and we know that Kh is equal to C alpha C square alpha square by C 1 minus alpha, which is your equal to, if one is quite greater than alpha, then we can write simply C alpha square, and so, or we can simply write OH minus is equal to C alpha. Since OH minus is equal to C alpha, your KH will be, and KH is equal to C alpha square, and so if I multiply this by C, both sides C, so this C into KH will be C alpha square, which is OH minus square, and so OH minus is equal to, OH minus concentration is equal to KH into C, KH into C, and KH we already calculate, KH is equal to your Kw by Ka. So, this equation OH minus ion concentration Kw by Ka into C can be used to calculate pH of the solution. We can do that here, minus log OH minus is equal to half log your Kw by Ka into C. So, half log Kw minus log Ka plus log C. This is with the minus sign. So, let us put minus sign here, and so POH will be minus log OH, and from this equation we can calculate what will the POH solution, and since POH plus pH is equal to 14, you will be able to calculate your pH of the solution. So, this is, so we discuss first salt of strong acid and strong base like NaCl, and salt of weak acid and a strong base. Now, we will discuss salt of strong acid and weak base. For example, we discussed about NH4Cl. Again, this is a soluble salt. When we put into the solution, it will break completely. So, this is your sea salt, then it will give you the concentration of NH4 will be also equal to sea salt. Okay. So, basically everyone goes to NH4 plus ion. Now, NH4 plus ion with water will give you NH3 aqueous plus S3O plus, sorry, yes, S3O plus. This is your reversible reaction. This is your reversible reaction. And so, you can write K H is equal to NH3 H3O plus divided by NH4 plus. And we know that NH3 in aqueous solution gives you NH4 plus into this is your OH minus ion in aqueous, and so this is your Kb. Kb is equal to your NH4 plus OH minus divided by NH3, and just now we calculated Kh, which is NH3 aqueous into S3O plus divided by NH4 plus. Again, if in this case we multiplied Kb into Kh, it will be going to be equal to Kw. If we know Kw and Kb of your weak base, we can calculate Kh, and once we know Kh, we can calculate OH minus ion concentration and OH minus ion concentration or H plus ion concentration. So, let us again write how can we calculate. This is NH4 plus H2O, NH3 aqueous plus S3O plus. Initially, you have sea salt 0 0 at equilibrium. This is sea salt 1 minus alpha, and this is C alpha, and so Kh, which is nothing but Kw by Kb, which just we calculated, is equal to C A square alpha A square, this is C 1 minus alpha, and if alpha is quite small than 1, we can simply write C alpha A square. So, C A square alpha A square is simply Kh into C, and this is nothing but H plus ion A square or H3O A square, and this is your Kh into C. So, H plus ion concentration can be calculated by taking a square root of Kh into C, a square root of Kh into C. And we know that Kh into C, Kh is Kw by Kb into C. So, it is quite easy if you understand how to calculate, how to derive this equation, how the ions behaves in the aqueous solution. It is quite easy to write an equation for hydrolysis constant in case of salt, and hydrolysis constant is related to your ionic product and your Ka or Kb. Once we know Kh, we can calculate your concentration of H plus ion or OH minus ion in the solution depending on which salt you have taken. and once you know H plus ion or H minus ion, you will be able to calculate your pH of the solution. So, for example, here we simply take minus log H plus, which will be give you minus half your log K W minus log K B plus log C, and this is your pH is equal to minus half, you see minus half log K W is your minus log K W is P K W, or simply you can write your P K W is, so minus half into P K W, and minus log K B is P K B plus log or minus half log C, half P K B plus half log C. This is the way we can calculate your pH of the solution if we know which kind of salt is present in the solution. Now, the last one is salt of your weak acid and weak base. Weak acid and weak base. For example, we can take the solution of ammonium acetate. Again, this is soluble salt. So, it can simply break when put in the solution. 100% it will dissociate, it will give you CH3COO minus plus NH4 plus. Okay. And when you put, if you think about how acetate ion will behave in aqueous solution, it will basically extract CH3COOH plus OH minus ion, and KH will be equal to your CH3COH into OH minus divided by CH3CO minus. When ammonium plus ion will hydrolyze, this in water will give you ammonia plus H3O plus solution, So, based on that, again you can write KH for your acetate ion and KH for your ammonium plus ion, and then finally you can calculate H plus ion the way I have done for other salts. So, thank you.